Second speaker, Professor Frank Ruger. He is a professor of fluid process engineering at Cornell University of Applied Science. His focus is on his thermal process technology, including membrane and wastewater treatment technology. Please, Professor Frank, do you hear me?
Okay, good afternoon. Can you hear me?
Yes.
Okay, and the sound is understandable, I hope.
We hear you.
Okay, great. So welcome to my presentation on future fields of membrane application. So as you may know, this is a broad field. So therefore, I will be focusing on especially circular economy and energy efficiency in processes with focus on the German situation. So in Germany, we have some societal issues that may be a little bit different from Egypt. So one of them is closely related to the demographic change. Other problems are related to the limited resources and the intended independence of suppliers of these materials and raw materials. And another point is energy efficiency. So I can sum up that we have to change our way of life, and membranes can contribute to this change in society and in the industry. So the main objectives that I will be showing here is material efficiency and green chemistry, so as to establish a sustainable and circular economy, which is part of our legal system nowadays. And the other point is energy efficiency, you all know, related to the supply and generation of energy. We have the problem of the emission of greenhouse gases. So we also need to focus on these points. And here I have a current photo of the River Rhine in Cologne, where I'm situated. And you may all think that Germany is a cold country with a lot of rain. So this may be partially right. So this summer, this is not right. And last summer, it was also not right. Here you can see the River Rhine has nearly disappeared. So also here in Germany, we feel the effects of climate change, and we must address these problems that are not only related to the industry, which does not receive now enough cooling water. It's also a problem concerning the transportation ways, because a lot of goods are transported on the River Rhine, and certainly it's also concerning the supply of the people with drinking water. So, well, at first, I would like to stress here an overview of the technologies or the applications of membrane technologies that have a close connection to our societal problems. So especially when it comes to the application, we talk about sustainable water. So which alternatives do we have for more efficient water treatment? How can we find alternative water sources and bring them in the appropriate characteristics of drinking water? We are talking about sustainable chemistry. We are talking about sustainable food technology, biotechnology, biofarm, chemfarm. And especially also we are talking about energy storage and conversion with the help of membranes. So, and another aspect is certainly also the development of new membranes. So you're the experts also in membrane development. So I'm only a guy who uses membranes and tries to get out the best of these membranes. So the question of membrane development is unfortunately not my field. Well, what I want to show you, because the time is also restricted, is 3 examples coming from my institute. So 2 of the examples are focusing on energy efficient production and the reduction of greenhouse gases. So at first, with the help of forward osmosis in wastewater treatment, and the second one is membrane distillation in an application in the pharmaceutical industry. So, and the third example will be concerning circular economy and the recovery of lithium from waste products. Well, when we talk about membranes as one option for the process industry, we can see here now that membranes as a whole, so it's a lot of different technologies, certainly, but membranes as a whole, they have a relatively small energy demand compared to, for instance, distillation processes. So this is what we need where it is possible and where it can be applied. We should think about shifting from the traditional separation processes such as distillation and come to more energy efficient processes using membranes. Well, here I give you an example concerning the forward osmosis. So you have already received a small introduction into this technology. So what is done in principle is that we have a feed solution that is circulated in a counterflow to a draw solution. The draw solution has a higher osmotic pressure and in principle sucks out the solvent, and in most cases this is water, and so the feed solution gets concentrated. Well, afterwards we have to work also on the regeneration of the draw solution, but well, the forward osmosis as a process is a low energy process because it works more or less at a very small pressure below 1 bar. We have rather uncomplicated technology, and from the idea we also have a lower fouling, but you know, every kind of membrane process, every kind of separation process suffers from fouling. Well, one of the focusing points for the development is the draw solution that should be found for each and every application. So we have different demands on this draw solution. That's water solubility, for instance, that's the osmotic pressure. It's the viscosity that influences also the operating costs, and it's other characteristics such as a cheap solution. The solution should not be poisonous, and it should be easy to recover. So not necessarily with the help of reverse osmosis, but with any other kind of separation technology. So, and what we did in our institute together with the company Miontech, where a PhD student is now working. So they tried to use the so-called aquaporine membrane. So that's a bio-based material that allows a specific water transport through the membrane. And he tested several draw solutions based on inorganic salts. And what we can see here is that different salts with the same concentration have different properties concerning the water flux from the feed solution into the respective draw solution. So for each and every situation, this should be measured, and then the best solution should be found in terms of water flux and in terms of a reverse flux from the draw solution. So next thing is membrane distillation. So we conducted several experiments together with two companies. So Deucom provided the respective modules. I can show you on the next slide the type of module. And the company Werner is a company that is closely related to the production of pharmaceutical grade water. So the idea was to find alternatives to the technologies that are now being used, that's reverse osmosis and distillation, and both of them have a rather high energy demand. And the question was, can't we use also membrane distillation, which has a smaller energy demand for the production of pharmaceutical waters? So in pharmaceutical industry, we distinguish between two kinds of waters. The first thing is the so-called purified water, and the other solution that has a higher demand on the quality is water for injection. So that's, for instance, used for any kinds of solutions that are in direct contact with the human body. So as you can see here, the respective parameters, they are set in the so-called European pharmacopoeia. This is kind of European guideline or kind of law. And so all the qualities that can be achieved by other technologies, they have to meet at least these respective parameters. And the next thing is that in the pharmaceutical industry, you need to have a permission to use a specific technology. So for the production of water for injection only, distillation and reverse osmosis are allowed. So other technologies are not allowed. And if you want to use other technologies, so then you have to pass a specific process that shows that this new technology is able to provide also the same quality under given conditions for a long time without any impair of the hygienic quality. Well, here you can see this kind of module. So it's a plate and frame module provided by Deucom, and the setup was so-called air gap membrane distillation. So here in this case, we have a hot feed on the one side of the membrane, and on the other side, we have an air gap. And after the air gap, there's a cold surface where the condensation of the respective steam takes place. Well, the material was polyethylene that we have used here, and we have used in this case for the tests an artificial heating of the hot feed. But for real life applications, the higher temperature could be provided by waste energy, and this makes the technology so interesting. Well, and here I give you two examples of results of our experiments. So here this is showing the transmembrane distillate flux. So the black line in the middle shows the average value indicating the effect of the feed temperature. So the cooling water was tap water, so a temperature of 20 degrees. And we use different temperatures of the feed solutions. And you can see the higher the feed solution, the better certainly is the performance concerning the distillate flux. On the other hand, we also tested some other parameters that are quite normal for testing in membrane technology. So that's the cross-flow velocity. So in this case, we could see that until a given point, the cross-flow velocity leads directly to a higher flux. But at a given situation, higher cross-flow velocity does not provide any more advantages. That's shown in the respective graphs here in the upper part. So that means there's a limit of the optimum cross-flow velocity for the operation. And most importantly, we also checked the hygienic demands, and we had two different possibilities to measure the bacteria counts. So the first one was according to the European Pharmacopoeia, and the second one was to the German drinking water laws. So as we can see here, so the bacterial reduction in the respective pharmaceutical water here meets the requirements. So the distillate here has 300 colony forming units, and the limits are in the range of 10,000 CFU. So that's what we achieved, and also the quality concerning the electric conductivity was better than required. For the higher grade water for injection, unfortunately, we exceeded the respective values. So the electric conductivity was more or less okay, but concerning the bacteria counts, we only achieved a little bit higher values. So in principle, we could show membrane distillation is able to provide good quality. And the next step would now be to optimize the energy demand. So here was also the idea from our student to use also a heat pump system, so as to lower the energy demand of this whole process cycle. So
2 minutes, please.
Give me 1 more minute. So last thing is the recovery of lithium containing solutions. So we are thinking in Germany of secondary sources now. That means lithium coming from lithium ion batteries. So we collect them, shredder them, and try to extract the lithium from this waste product. And when it is available in a liquid form, we could, for instance, use electrodialysis for the recovery. So, and these graphs show the performance. So we can see that here the orange curve shows the behavior of lithium chloride, and the brown curve here shows the behavior for the concentration of lithium hydroxide. And as we can see here, the respective process and the overconcentration would be much faster if we transfer the lithium into lithium chloride because of, as we can see here, the stronger slope that we can achieve with this kind of solution. So conclusions that I can draw is that against the background of the global situation and the demands of the German society, membrane technology is quite good fitting into these aims, because many of the technologies have either already proved their ability, or they or experiments have shown that they have the ability to provide good industrial solutions. But on the other hand, we have talked about circular economy. We also have to check the possibility to recover the membranes and to produce membranes also out of materials that have a lower impact on the environment. So the way is not over. So there's a lot of work to be done. So this is especially focusing on the effects, on the aspects of membrane production. So thank you for listening. And well, do you have any questions?
Any questions? Thank you, Dr. Rogener. Actually,